Good morning to everyone. So today's class is about Kepler's law of planetary motion. Okay. So the scientist Kepler describes about the planetary motion. Okay, planetary motion, and he described few laws, nothing but three laws about the planets, about the planet size of the planet and the area of the planet, and also the how the planets revolves around the sun. Okay, all these explained by the Kepler's. So all the three laws can be explained detailed in this session. Okay. Now Kepler explained about the planetary motion. He proposed three laws. Now in that, the Kepler's first law is that Kepler's first law is known as law of orbits. Okay. The Kepler first law is also known as law of orbits. Nothing but what the first law described means the path of a planet in an elliptical orbit with sun as its foci. It's nothing but suppose let a planet like Earth is there. Okay, so the planet revolves around the sun. Okay, the planet revolves around the sun by making as sun as its center. The planet revolves around the sun in an elliptical orbit. So these laws is explained by Kepler's first law. Okay. Now the path of an elliptical orbit, the path of a planet in an elliptical orbit with sun as its foci. Means otherwise we can describe it as the planets revolve around the sun by making its center as its center or as its foci in an elliptical shape. Okay. So this is an first law. So in the class itself we described or we deducted the first law derivation. Okay. Now moving to the second law. This second law is known as law of areas. While the first law is known as law of orbits, which explains about the elliptical orbit, means how the planets revolves around the sun in a particular orbit. Okay. So these explained by the first law. Now the second law is law of areas. Means the second law clearly explains about the area which is covered by the planet around the sun. Means the second law can be explained in detail as the radius vector drawn from sun to the planet. Okay, sweeps out the equal areas in equal amount of time. Means let us consider a radius point from sun to the planet like Earth. Okay, let us consider a radius vector from the sun to the Earth. Now, if an Earth moves in an elliptical shape according to the first law, Earth moves in an elliptical shape following an elliptical path around the sun. Let be a certain point. Let it be a certain point P. Okay, let be a certain point P, and let be a certain point P dash. Okay, let 0 be the O be the center of the sun, and P be the planet. If a planet moves around the sun, okay, the vector is drawn from the sun. So wherever may be the planet may be here or here or here or here. It sweeps out, it covers the equal amount of area, in equal amount of time. Means this law clearly explains about the speed of the planet, okay, and also distance from the sun to the planet. Okay, while the first law is explained about the path of the planetary motion. Right? Now second law is explained as it explains about with how much speed it moves in an elliptical shape, or what is the distance between the sun to the planet while revolving the planet around the sun. Right? Now if we move to the derivation part of the second law, we consider that let O be the center of the sun and let the planet be at point P. If a planet moves around the sun in an elliptical shape, okay, in an elliptical orbit, it makes an angle theta, d theta. So now we can draw two vectors from the sun. From O and P, R plus dr is a vector, and O and P dash R be the vector. Now dA by dt is equal to half r square d beta by dt. Now let us consider this entire term is equal to some constant h. Now dA by dt is equal to h by 2. Means h is a constant. Means the differentiation of a particular thing is constant means that a is termed as constant. Now according to the second law we can also say that the area velocity will be constant. Wherever may be the planet may be here or here or here, whatever may be the distance, but it covers the equal amount of area in a particular equal amount of time. This law is explained in a Kepler's second law. Now moving to the third law, Kepler first law is law of orbits, second law is law of areas. Okay, now the third law is known as harmonic law. Means the third law explains about the time period of the planet. Okay, the time period of the planet. Means according to the third law we can term as the square of the time period of the planet is directly proportional to the semi-cube of the semi-major axis of the orbit, where A is the semi-major axis, where A is represented as, where A is nothing but semi-major axis, right? Now first law is about the law of areas which describes about the path. Second law is about the law of areas, okay, which describes about the area velocity. Nothing but it keeps the area is constant. Means it also explains about the distance from the sun to the planet. Now the third law is explains as the time period of the planet. The square of the time period is directly proportional to the cube of the semi-major axis of an orbit. So this is a peculiar Kepler's third law. Okay. Now it also explains about the size of an orbit. Okay, size of a planet. Now that how the time period is calculated. Formula for the time period is area speed sounds in one revolution to the ratio of area velocity. So now the t is equal to pi ab, where pi is a constant. Okay. So the amount of semi-major axis is A and B is the semi-lattice vector. Okay, semi-major axis, A is the major axis and B is the semi-minor axis. Now, what is the area velocity from second law? The area velocity from the second law is h by 2. Now, t is equal to pi ab by h by 2. So, in the first law, we know that the semi-lattice vector L is equal to h square by mu. But we derived finally as the semi-lattice vector as b square by a. Okay, the semi-lattice vector is nothing but square of the minor axis to the ratio of major axis. So b square by a is equal to h square by mu. Right? Implies we can calculate the h value, where h square is equal to b square mu by a and h is equal to b of under root mu by a. Now substitute this entire h value in this equation 1. Now t is equal to pi ab by b by 2 the root mu by a. B gets cancelled. Now the numerator to the denominator. If you move to the upperwards, it becomes a numerator. Then t is equal to 2 pi a by mu by a under root. Okay. Now if we square on both sides, t square is equal to 2 is nothing but 4, pi is nothing but pi square, a is nothing but a square. But the denominator we have 1a. Thus after squaring the root gets cancelled. Only one a we can remain. So that a if we move to the numerator, a square plus 1, a cube, then mu square will be there. So these 4 pi square by mu square, if you term as a constant, then we can write directly as t square is directly proportional to the a cube. So once again carefully listen. The first law is about the law of orbits, which explains about the path of a planet, how the path will be. Means explains as a planet revolves around the sun. Okay, as a planet revolves around the sun by making as its center in an elliptical orbit. So it purely explains about the path of a planet. Right? Now the second law is about the plus. Means it clearly explains about the distance between from the sun to the earth, and also how much area will be covered while moving around the sun. So it also describes how much of area will be covered in a particular elliptical shape when the planet moves around the sun. Then also it can also state that area velocity will be going to be act as a constant. Now third law is nothing but it's an harmonic law, means it explains about the time period and also about the size of an orbit. Okay. Now the square of the time period is directly proportional to the cube of the semi-major axis of an orbit. So this is the derivative part and the pure explanation of the Kepler's laws of planetary motion.